Okay, I'll try to explain this to help you understand better what's going on. Here's the cylinder. Rough sketch with a radius of r, height of h. And if you picture cutting this open along the side and then laying it out flat, you kind of get a rectangle that looks like this. And this dimension is really this circumference spread out. So the circumference of a circle is 2 pi r, and the height is still h. So the lateral surface area of the cylinder is 2 pi r times h, length times width. Okay, and of course there are circles at the top and the bottom, and their areas are pi r squared. So the area of the top is pi r squared. I used a little r here. So the cost of the top is 0.05 times pi r squared, 5 cents per square centimeter. I wrote the 0.05 as 1/20th pi r squared because I don't like to deal with decimals. The area of the bottom is still pi r squared, a circle. The cost of the bottom is also, or is 4 cents per square centimeter, which is 1/25th. And now, well, the lateral surface area we've seen is 2 pi r h, but we want to get the cost function in terms of one letter, probably r. And that's why they gave us this piece of information right here. The volume of the cylinder is supposed to be 500 cubic centimeters. The volume of the cylinder is pi r squared h. We want the volume to be 500. That allows us to get h in terms of r. Just divide by pi r squared. So there is what h is in terms of r. So the lateral surface area is 2 pi r h, but I'm going to replace this h with 500 over pi r squared. And I can see that the pi cancels out and one of the factors of r cancels out, and I get 1,000 over r. That's the area of the lateral surface, or the sides of the cylinder. And each of those square centimeters costs 4 cents, or multiplied by 1/25th, which is 40 over r. So now with all of this, that allows us to create the cost function. C depends on r. We add cost plus this cost plus this cost. We will have the cost of the cylinder, depending on the radius that we set. Okay, and if we combine these first two terms, since they both are dealing with pi r squared, we get 9/100ths. Just get a common denominator of 100. And write plus 40 over 40 r to the minus 1. I write it that way so that we can take the derivative. Now you've got a function depending on one variable. How do you find out maximum and minimum values for a function? Well, you take the derivative, set the derivative equal to 0. You can think of that. That's where the graph has a horizontal tangent. So that'll either be a maximum or a relative minimum or a relative maximum. So when does this derivative equal 0? When 9 over 50 pi r equals 40 over r squared. And we'll go to board 2 to take a look at that. If we cross multiply, we get 9 pi r cubed equals 2,000. R cubed equals 2,000 over 9 pi. So this is what we want the radius to be. I'll quickly share my screen. Go to Desmos and let you take a look. So there's r, the cube root of 2,000 over 9 pi. There's h, 500 over pi r squared. And look, the volume of pi r squared h, 500. Okay, here's your cost function. And this is the graph of that cost function at when x is greater than 0, which x stands for the radius. And there's r comma c of r. There's the minimum. You can see that's a local minimum. It's actually a global minimum when x is greater than 0. Okay, hope that helped. If you have any questions on that, post a comment.